Hi and welcome to this new MATLAB seminar. I'm Alberto and I am one of the two MATLAB ambassadors at Polytechnic of Milan. Today we are gonna speak about MATLAB and ROS, and in particular this is the third episode of the series MATLAB and ROS Complete Overview. In the past episode we see the hardware connection and the hardware itself of the robot, the kinematic and odometry. Today we are gonna look about the local planner and the mapping, and in future there will be an episode about the global planner. So let's go ahead and see what this presentation is about. We are gonna speak about the pursuit control that last time was just introduced. Then the remote controller, so a fast way to control the robot by ourselves. Then the map acquisition, so how to acquire data from the robot about the environment. And then last, how to merge this data in order to acquire and obtain a complete map. So let's start. The pursuit. The pursuit control is a tracking algorithm that in particular computes the angular commands in order to move the robot from the current position to some look ahead position. What does it mean? It means that the robot is in a particular position known by the pose information, so x, y and omega, and want to move to a newer position decided by the path that is defined by the waypoints. The pursuit control will generate the control action of v, so the linear velocity, and the omega, the angular velocity. But how this controller works? Okay, so the robot at the beginning is in point P1, so the starting point. Then it want to go in point P2, and so on, want to move to the other position, so let's say P3, P4 and P5. The algorithm first compute the connection between these points. So in particular, use a Pythagorean algorithm to calculate the shortest path to connect these points. And then, by using the look ahead distance, that is the main characteristic of this controller, can calculate how the robot has to move. In particular, the look ahead distance compute the trajectory, and so the robot, the controller, calculate the angle, so the omega and the v, in order to move the robot in some defined position, that is the intersection between this circumference around the robot and the path that has been calculated before, so the lines that connect the different points. As you can see in this slide, the robot in red point to a look ahead point, so the orange one, and try to reach it. Each time stamp, so each time the program evolves, compute a new position, and so a new control action. So, speaking about the circumference around the robot, we can have a small circumference, so we will have a better tracking of the path, because the robot will move very little away from the desired track. So, for example, in the let's say waypoint, it will pass through the waypoint because it has a very small circumference, but it can generate some oscillation of the robot. On the other hand, if we want to use a more bigger circumference, we will have a look ahead distance far away, and it will generate a smoother trajectory. In particular, this will be helpful if we want a smooth path in order to connect different waypoints. In particular, as we can see, this bigger circumference does not allow the robot to pass through the waypoint. So if the waypoint is a point that we must pass through, this is not the solution, correct? It's better to have a smaller look ahead. If we want a smooth movement, so we want to go from a point A to a point B, keep in mind that the robot has to move as linearly as possible, a bigger circumference will be the right choice. Okay, now speaking about the remote controller. The remote controller is a key feature in order to control the robot without the algorithm. But before, let's look at how the structure of the overall system will become. Okay, we have firstly the part relative to the automatic control. So the purpose that we just discussed about. Then we have the possibility to use the remote controller, so a controller that will drive the robot, and us, let's say the human, will decide which trajectory has to follow. Then, through a selector, we can discriminate if we want the automatic one or the remote controller, and then through the kinematic and the omega left and omega right, we'll compute the output. So, speaking about the joystick input. Joystick input means that we have a controller, a remote controller, that can produce some set point that the computer will transmit to the robot. In particular, we will use the joystick input special block that MATLAB provides in order to acquire this information and elaborate in order to generate some useful signals. In particular, the joystick input allows to get information about the axis of the controller, so let's say some analog values like from 0 to 1 or from 0 to -1 with lots of an analog quantity, so with lots of steps. Or we can acquire the button of the controller, such as in the controller if you press a key, okay? And so we can acquire the different buttons. Then, lastly, if we have a special controller that also can give us the feedback of the force, this block allows as input the force feedback. So we can select a set of forces that the controller have to give us. So this block is very powerful and allows a very complex and variety of input-output in order to be able to interface with any controller, such as the classical Xbox or PS controller, but also more sophisticated one like for simulators or let's say more professional one. So let's see how it is implemented in Simulink. Firstly, we have the pose of the robot. So as we discussed in the last video, we can know exactly the pose of the robot through the odometry. Second, we have the possibility to have the remote controller. So we read the information about the axis, we do some operation in order to clean the data, and then we provide V and omega manually in this case. Then we have the pursuit, taking the input information, the pose can generate the V and omega for the automatic driving. Then we have the selector that through the switch that we can see manual automatic can be set if we want the automatic or the manual commands. And then through the kinematics and the output we can generate the information that the robot will take to be able to move. So that the ROS environment loaded on the robot can collect and then translate into some useful action. Now we will speak about the map acquisition. This is very important for the overall architecture of the robot because we need to know the environment in which the robot is. So in particular, we will see how to acquire lidar data in the system. Okay. In this slide, I want to recap a little bit what is a lidar. Lidar is a sensor that can acquire the distance from the object in the environment. In particular, the device itself, it's a device that contains a laser that can send a beam on the walls and know exactly how long it takes to come back. So by knowing the exact speed of light, it can calculate the distance of the walls. In particular, in the picture you can see in the below the device, you can know exactly, you can understand how it performs. So it sends a sequence of beams by meanwhile the the emitters is rotating, so it can acquire different sectors and different distances during a complete turn, and it will generate for each turn a set of ranges. This set of ranges will be then stitched into a vector and then published in the /scan topic. So the particular node that will run on the robot will acquire this information, do some processing, and publish a range information. This range information is matched with the angles, so we know exactly that from 0, 1 to 360 degree, we have for each one of these degree an exact information about the distance. So again, I want to stress this topic. The lidar will turn and send a set of beams that will go and come through, and by acquiring the time of flight, it computes the distance. These ranges will be then stitched into a vector. This vector is called ranges and will be used to compute the map of the environment. Okay, so moving on Simulink, we will have the input of the pose that we discussed last time. This pose will be a set of data of x, y, and omega and represent the position of the robot in the environment, but we don't know exactly the environment. We know only how far and how the robot moves in this environment, but we don't know the walls or any other things inside the environment. With the lidar, so the /scan information, we can acquire the angles and the ranges, and all this process will be executed at 100 Hz in order to know and acquire a significant amount of data in order to then be processed. This data will be stored meanwhile the execution on Simulink. Now we'll switch on a little demo, and I will show you how to acquire this data on the Simulink. Here we are on the demo part. So we have here the Simulink, and we are in a test environment playground. Okay, so first what we have to do is select manual on the switch, and then by connecting to the correct Wi-Fi network of the robot that you can see here, okay, we can then select ROS network, okay, import the correct IP of the robot, the port, and click test. Okay, good, we have the connection, we are ready to run. Okay, we can click run, and the code start compiling. It will take some seconds. We now put the laptop here. Okay, we take the controller that we have just discussed about, and by the use of the Joystick Input app controller block, we will be able to control the robot. Now the code is running. Okay, and we can see that the robot now can be moved. Okay, now it's also acquiring data. So by means of the lidar that now is running here, you can see it's spinning, we can move the robot and it's projected the beams in order to acquire the data. So now it's moving toward the end of the wardrobe, and now it can read the distance from the wall. Now by moving this robot around, we can acquire the information about the room and construct the map. So now let's go back to the presentation and see what we can do with this information. We have now to speak about the last part, merging this data that we just acquired. This is an operation not so trivial because we acquire a very big amount of data and we need to stitch them together. So, as I just explained, we have the angles, the outranges, and the position. they must be downsampled. So we need to reduce the information because we don't need to have 100 Hz information because it's too much. We don't move the robot so fast. By downsample it, we reduce the information to 1 Hz. So 1 scan for each seconds. Then by using these ranges and the pose and the angle information, we can generate the set of information called scan and odom, that stands for odometry and scanning. This information will be used by the specific app that I will show you, called SLAM Map Builder, that will generate the overall maps. This part can be processed into the application, but we decide to use some MATLAB code in order to speed up the code. And as we can see in the few lines, we take the angles that is standard, so we generate it through a lean space. We then do a downsample of the information, one every 100 sample, and we put it into the scan and the odom vector. Then we call the function SLAM Map Builder with the topics scan and odom. Now we can move to the application, and the application, as we can see, is very user-friendly. It allows to import the data and to tweak the SLAM settings. The feature of this application are the incremental scan matching. So if we have, as usual, let's say a set of information, in this case 244 information, the process will go through all this information and match them in order to generate the best map. Then we have the loop closure, that is another feature that can allow us to compute some closed path for the robot in order to be sure and correct the odometry information that suffers of some drifting due to the non-idealities of this type of acquisition. Now let's move to the MATLAB environment and see how it works. So here we are on MATLAB. Let's run this code and see what are the steps in order to compute a map through the output that we just collected. First, run the script. Okay, it will acquire the information from the output that we saved from our last test, and we'll open the SLAM Map Builder. SLAM Map Builder that calling it through the already scan and odom information will be already set in order to be to run the information. You load the information through the import. We can select import from workspace or input from ROSpec as we wish. In particular, we can simply click build, and we will see that we have a set of information here, 129 different steps. So being this 1 Hz, we have 129 seconds, means about 2 minutes, and that is the time that takes the robot to go around the room. Okay, as we can see, the software, the algorithm is working, and it will computing the matching of the different scans. In particular, here is on the right part, and compute the right part. When we will move in the other part, and as we can see right now, we are going through the narrow part, we will then boom, generate the information about the other part of the rooms. So we can only reconstruct the rooms that, of course, we see with the robot. So again, it takes some seconds in order to compute the overall process, and it will generate the map. Perfect, we have just generated the map. We can now export this information to the workspace. Okay, we can call it my occupancy map. Okay, we can now close this. Okay, and if we want to see this map, we can simply type show open my occupancy map. Boom, here we are. Our occupancy map. Okay, now go back to the presentation, and I want to thank you for this, for being here in all this presentation. I try to explain every part. If you have any question, leave a question down below in the comment section and we will answer it as soon as possible. Or if you can't, contact us on Facebook or Instagram. Or if you want to reach us directly, this is our mail. Okay, don't forget to subscribe to our channel and leave a thumb up if you like this video. We will soon release new video about the last part of this series, and the other colleagues will publish interest topics about the MATLAB environment. See you next time. Bye bye.